Okay, so morning everyone. Week 9. Yeah, week 9, lecture 1. Yeah, last 2 weeks, we're sort of right at the end of this course. A few things to remind you of. We've got your lab 5, which is due tomorrow. This week you'll be working on lab 6. Now, just a reminder, we pick your 5 best lab scores. Of course, that doesn't mean we are encouraging you not to do lab 6, but just a reminder that we only pick your 5 best scores. So there is some flexibility for you to not submit one lab, or perhaps, we'll leave that for you to think about. The other thing, of course, is the assignment. Do note the deadline is hard. There won't be any extensions. It is due by noon, Friday, 19th November. So the Friday of next week. We do have lab consults running. So if you need help, you can, of course, go there. And another very, very, very important note, actually, we, of course, understand a lot of you will be writing your code on your own machine, which is perfectly fine. However, remember that we can't test your code on your machine. We can only test it on a common platform, which is essentially the CSE server platform. So you have to make sure your assignment works as expected in the VLab environment, right? Because that is how your assignment will be marked. So please, please, please take the time to thoroughly test it before you actually submit. Because we always get a few emails later saying, well, my assignment works on my machine, but it doesn't work on VLab. Well, we warned you, right? We've been warning you for quite some time now. So really, the ball is in your court, essentially, to make sure that it actually works. Typically, you won't find huge differences. There might be 1 or 2 minor differences because of all these variations in the versions, libraries, and so on and so forth. So might as well make sure, right? It probably only takes you, I don't know, half an hour, 1 hour, or whatever, to test it in VLab. So please do that. And then your final exam has been announced. So it's going to happen on Monday, 6th December in the afternoon, luckily, unlike the last midterm. And I will add a lot more information about that by next week. So this link, which is not yet visible to you, will be populated similar to what we had with the midterm. So there's Matt is saying there's some OS error interpretation differences. Yeah. So yeah, I think these are some of the things you need to be aware of, right? So just make sure you iron out those differences. William is asking, will there be a sample exam? Yes, certainly there will be. It will all be linked through the final exam page. I'll probably set that up by end of this week, latest early next week. So you should have all that information up there. Okay, so let's get cracking. We started looking at the link layer. Oh yeah, before I get to that, also a reminder to complete the my experience feedback. I think this should be now open. It opens today, I think. So we would greatly appreciate if you could provide us some feedback, things that you like, things that we could improve, because it helps us improve the offerings every term, right? We take your feedback seriously. I mean, just a couple of terms back, we were still using the web CMS forums. Since we've gotten feedback since last term, we started using Ed, and I think that has been a very positive change, right? Then last time we had some feedback about providing some additional video on multi-threading. So that's again something we've done. So we are constantly trying to improve this course. So certainly welcome any feedback you can give us. So we started looking at the link layer towards the end of previous lecture, and just quickly I'll recap what we looked at. So essentially the link layer is responsible for moving your packets across within a subnet essentially, right? So far we've been looking at the global scale, particularly when we talked about routing, we were looking at how to, for example, figure out end-to-end paths. Here, we are only going to focus on a subnet essentially, or essentially effectively a link, right? Basically, how do your packet moves across individual links? So in that context, every device that's pretty much connected to the internet will have a link layer running on it. So there's no real distinction between whether the device is a host or a router, right? In the context of the link layer. Switches are a bit different, and we'll look at link layer switches in the second lecture of this week. So for now, let's just call everything as nodes. And then, of course, we have the communication channels, the links that connect adjacent nodes, and they could be broadly of three types. Essentially, you could have a direct wired link, you could have a wireless link, which could either be Wi-Fi or cellular, and you could have what's referred to as a local area network. So that's essentially a Ethernet network, which is almost always a switched network, like what you see here. So this is something we'll look at in the second lecture this week. And a link layer packet, again, remember the convention we use. We refer to a packet using a different name at each layer. So you may recall layer 4, it's a segment, layer 3, it's a datagram, and layer 2, it's a frame. So effectively a segment sits inside a datagram sits inside a frame, right? And the link layer will add its own headers. So this was just a sort of nice analogy to explain the fact that as your messages are moving across the internet, they're very likely encountering different link layers along the way, right? So you might, for example, your packet may be sent over a Wi-Fi link on the first hop, Ethernet link on the next hop. Then maybe this what's called a SONET link, which is a link layer used by direct the links that connect routers to each other, which we won't get into in this course, but that's another link layer, right? So effectively, as your packet moves hop by hop, it is possible, not necessary, but possible that different link layers are used at each of those hops. And what that means is there might be some differences in the services that you may encounter. And one clear difference there is whether or not the link layer provides reliable transfer of data, right? So not all link layers will actually do that, and we'll talk a bit about that in just a minute. So some of the services the link layer performs are framing. So this is effectively encapsulating the datagram into a frame, adding certain headers and trailers. I'll talk a little bit about framing when I get into the Ethernet protocol, but remember, essentially your packets are transmitted as bits on the actual links, right? So when a receiver receives this frame, it should know what is the starting point of the frame and what is the ending point of the frame. So there's some sort of preamble that's added, and there's some trailers that are added at the end to effectively tell the receiver that, hey, this is the start and this is the end of the frame. Right? A second function that might be performed is what's referred to as channel access. Now, this is again not required on every link layer. However, it is certainly required on a link that is a shared link. So some examples include cable, right? So cable networks are actually shared. For example, if your internet is provided through a cable provider, the actual data rate you might experience can vary depending on how many other users are on the network, right? Similarly, Wi-Fi, if there are a lot of other hosts connected to the same access point, then the effective data rate that you get will reduce. So in these kind of networks, it is important that there is some arbitration on who gets to transmit, because if two nodes send to another node at exactly the same time, their packets will actually interfere with each other at the receiver, and the receiver will not be able to interpret either of those packets. So we'll talk a little bit again about this a little later today. So we need some sort of protocols to arbitrate that access. Next, we'll briefly talk about MAC addresses and how they're different from IP addresses. We'll probably do that on Wednesday. Now coming to reliability, right? So reliability is a potential service a link layer could provide. Now the mechanics of that we've already looked at, right? If you recall, we spent quite some time on the whole concept of reliable data delivery. When we looked at the transport layer, you might recall discussions on using sequence numbers, acts, timers. So all those concepts can be used, but the real question is, do we actually need to implement this at the link layer, given that it is already implemented in an end-to-end manner, right? Particularly in the context of TCP, which already takes care of these errors. Because in the end, if there's an error, one of these routers will drop that packet, and the packet is essentially lost. So eventually that will lead to either triple duplicate acts, or it will lead to a timeout, and the TCP sender will eventually retransmit that data, right? So now the question is, given that, do we still want the link layer to do a retransmission? Now the decision here really depends on what is the likelihood of bit errors, right? If the likelihood of bit errors is very high on a link, then perhaps it is okay to have this extra or repeated functionality, because remember, this functionality is already implemented on an end-to-end basis. So if we were to implement it at the link layer, we are kind of repeating, we are implementing reliability in two places, right? So if the link has very high probability of errors being introduced, then it perhaps makes sense to add this extra overhead, right? And this is precisely what's done in the internet. So on wireless links, which are more prone to errors than wired links, reliable delivery is actually enabled. On all wired links, the likelihood of bit errors is extremely low, extremely low. So there is no benefit to then implement reliability on wired links. So that is the general convention, right? Now you might wonder, okay, if the bit errors are high on wireless links, why do we still, what is the benefit of implementing reliable data transfer? Well, I mean, imagine imagine an end-to-end path, right? So you might have an end-to-end path like that, right? So multiple routers, say 3 routers along the way between the source and the destination. And we already know that, let's say we are using TCP. So on an end-to-end basis, we will have, if a packet gets dropped due to an error, it will get retransmitted. However, if the probability of these errors is high, right? Having the ability to retransmit right here on this immediate hop where these errors are happening is much more, is a quicker way to react and retransmit those packets rather than waiting for the end-to-end protocols to kick in, right? Because it takes some time for these duplicate acts to come, or it takes some time for the timer to expire. So a faster way to recover from those errors is to allow the link layer to actually do the retransmissions if errors are detected here, right? So that way we can react to errors much faster, knowing that the likelihood of errors is high. So that's the reason this functionality could be repeated on wireless links, but it doesn't make sense to do that on wired links given the reduced chance of errors. Some other functions the link layer can provide is framing. So this is the flow control, which is something we've already looked at. Error detection. So now this has to do with actually detecting that there was an error in the first place, because if you want to do reliable delivery, you of course need to detect errors. Even if you don't do reliable delivery, there is a benefit to detecting errors, because if we detect such an error, then there's no point forwarding the packet further, right? And you might wonder, why are errors caused? Well, this could be due to various physical artifacts like the noise in the environment, what's referred to as attenuation. So as the signal travels further, particularly on wireless links, the power of the signal reduces. So it's like when you're shouting, right? If someone is shouting very close to you, you can hear them. But if they're, say, several meters away, even if they're shouting, you might not be able to hear them because their sound propagation simply drops as you move further away. So the same thing applies in the wireless context. If you're transmitting something, a receiver may receive it fine if they're close, but if they're further away, then they may not actually receive the complete signal, right? And there could be other interference in the network. So that's the reason we need some protocols to detect against errors. One step further could be where we consider error correction. So not only are we detecting errors, but we actually precisely identify the bits that are erroneous, and then we go and correct them. Now, this is much harder to do than this. We'll talk briefly about that a little later today. And then finally, whether or not the link layer can provide half duplex or full duplex service. By full duplex, we mean both endpoints can send data to each other simultaneously. Half duplex means only one of them can send data at any given time. So typically wireless links are half duplex. So at any given time, your device can either send data to the access point or receive data, right? Whereas typically wired links are full duplex, right? Okay, so let's move forward now to talk about where the link layer is actually implemented. So it's of course implemented in each and every host, but within the host, where is it actually implemented? So as we've seen, the transport layer and even the network layer is actually implemented in the operating system. How about the link layer? Well, the link layer is actually implemented across, it's like a combination of things. So part of it is in software, part of it is in what's referred to as firmware, and part of it is actually directly implemented on hardware. So there are these link layer chips, so effectively Ethernet chips or Wi-Fi chips, which are directly embedded on the motherboard. In the olden days, I remember when I was at university, we used to actually buy these cards, like a card, and slot it into our desktop. Desktops were pretty big in those days. So there were these slots where you could slot in these sort of wireless cards or Ethernet cards, right? And these cards actually implemented part of those protocols. Now, these days, all of this is directly embedded on your motherboard. And there is typically, it's connected to the host bus that connects all these chips to the CPU and memory, right? And this also, that hardware chip will also implement the physical layer, which we are going to skip in this course. So that takes care of the actual modulation and transmission of the data. And then if it's a wired link, there would of course be a connection to an Ethernet port. If it's wireless, then it's just a radio, basically a transceiver that's transmitting and receiving, right? So effectively, it's a combination of hardware, software, and firmware. Right. So as you see there, the link layer is actually split up. Part of it is actually running on your computer itself. Part of it is directly running on the hardware, right? So when a datagram is pushed down, the link layer will encapsulate the datagram by adding certain header fields. So these headers will of course depend on the specific layer, but effectively these will be additional fields for implementing error checking. If the protocol implements reliable data transfer, flow control, and so on and so forth. And the frame gets pushed out. When it reaches the receiver will then first check if it's the correct destination. It will then pull up that frame. It will examine those header fields and execute the corresponding functions for whatever has been implemented, and then extract the datagram and pass it up to the network layer, right? There's a question, is there one implementation of the layer per physical network device? James has asked that. So yes, that is correct. So for example, my laptop here, it's currently it's got an Ethernet chip, of course, and it's also got a Wi-Fi chip, right? So it's implementing both those link layers, and of course, the appropriate link layer is used when data is sent on a particular link. Laptops still have network cards these days that pop into the M2 slots. Yes, that's correct, Dharam. So yeah, you still have those cards sometimes. Okay, so let's now start looking at error detection and correction. So let's first look at this conceptually, and then we'll precisely see what is actually used in real link layers, right? So some of this initial discussion is again conceptual. So what is the idea here? Well, we are sending out a datagram onto a link, which is likely to have bit errors, right? Now, the only way you can do error detection and correction is by adding some extra redundancy, which are basically indicated by EDC. So these are some additional bits that we add. And then we send this combination of D and EDC out. What pops out at the other side is what we refer to as D prime and EDC prime, right? So potentially either of these or both of these could have bit errors, right? We can't assume that the EDC bits cannot be corrupted. That is not a fair assumption, right? Because if the link induces errors, it can induce errors anywhere in the frame. Then we need to, of course, implement some algorithm, which will first determine how these bits are created. And then based on that, this algorithm will look at both these parts and then try to infer if there was any bit error or not. If not, it will pull out the datagram, pass it up to the network layer. If not, it will detect an error. Now the question, what happens when you detect an error? Well, if this link layer protocol implements reliability, then very likely it's going to send an ACK or something like that, or an ACK, whatever is implemented. If not, it's going to drop this frame at this point, right? Because there's no benefit to reading this frame in the network layer because we know it has errors, right? Now, mind you, all the error detection algorithms we'll consider today are not actually 100% reliable. They do provide certain guarantees, but it's not like they'll detect all sorts of errors all the time, right? However, the way they are designed, the likelihood of those errors happening is so low that almost always in practice, you can assume that it will detect almost all errors. But at the same time, being aware that occasionally it might not detect errors. Now, of course, intuitively, the more bits you add here, the better the detection and correction. The other option is if you don't want to add too many bits, then you make this protocol itself highly complicated, right? So you use a better protocol, which can still use less number of bits, but still achieve a good reliability, right? There's a point here about the larger, if you have more EDC bits, then the potential errors will also increase in the EDC. Yes, that is correct. So in fact, you'll see later that the actual protocol used in the link layer actually is one that doesn't introduce excessive EDC bits than required, but it is a little more complicated protocol than some of the other protocols we'll see first up, right? So there's essentially that trade-off, whether you want to, because EDC bits also add errors, overheads, and then as Dharam pointed, you're also likely increasing the probability of errors in those EDC bits themselves. So let's start off by looking at a very naive scheme, which is called parity checking. This is very intuitive. The idea is fairly simple. In this first instance, we are using a scheme which just adds one extra parity bit. And the idea being, so you can either have an even parity or an odd parity. In this example, I'm using even parity, which means we look at the number of ones. We essentially make sure that the total number of ones in this whole frame, which includes the original data plus this parity bit, are even. So if you look at this message itself without the parity bit, how many ones do we have? 1, 2, 3, 4, 5, 6, 7, 8, 9, right? So we have 9 ones, which means they are odd. So the parity bit is set to 1. If the number of ones were even, for example, let's say this last bit was a 0 instead of a 1, then the parity bit would have been a 0, right? Assuming it's even parity. If it's odd parity, you use the reverse logic essentially. So what this means is the sender will do this. It will effectively do a modulo sum of zeros and ones. If the end result is a 1, it adds a 1 here. If the end result is a 0, it will add a 0 here. And then send this entire message out. The receiver knows it's even parity is being used. So it will do the same thing. It will basically do a modulo sum of all the bits. If the end result, modulo 2, I mean, if the end result is a 0, it knows it assumes there are no errors. If the end result is a 1, it knows there's some errors. Right? Now this can, mind you, this can only detect single bit errors, right? So if you think of some simple examples, let's say, for example, if these 2 bits were erroneous, right? So if this was a 1 and this was a 0, then you'll quickly see that this will not actually detect an error because it still matches the even parity logic. So the receiver will actually think this was not erroneous. However, if 3 bits are in error, it will still be able to detect that, right? So effectively it detects either 1-bit errors, 3-bit errors, 5-bit errors, and so on and so forth, right? But it can't detect 2-bit errors, 4-bit errors, and so on and so forth. So clearly this is not you probably don't want to use this in practice because this is highly error prone. So can we do better? Well, you can. What you could do is, rather than just adding 1 parity bit, you could break up your data and organize it in a matrix like that, and then run parities for each row and each column, right? So we are effectively adding all these bits which are extra, right? So we have increased the number of EDC bits, but this is now going to allow us to detect a lot more errors than you could with just 1 parity bit, right? So the same concept applies. You either use even or odd parity. In the examples, we are using even, and then you run that same logic on each column and each row. Right? So here's an example where there are no errors, right? So these are the parity bits. Oops, this line is drawn a bit incorrectly. I'll try to fix this up, but effectively it should be here, right? So these are the row parities, these are the column parities, right? In this example, actually, it's using odd parity, is it? How come this is a 1? Seems to be, this should be a 0. Am I right? Yeah, I think I've made an error there. Yeah, that should actually be a 0. Because it's saying there's no errors. That's why I'm thinking that this means there's no error, right? So if you look at the other columns, yeah, I think that should be a 0. Yeah, this is even parity, right? And now this is showing you an example where this should also be a 0 as per that logic, right? This is showing you a case where, let's say, this bit was in error. So this 1 here was flipped to a 0. So in this case, you'll notice both the row parity and the column parity will be erroneous. So in fact, in this case, you can actually identify which bit was in error, and you could actually correct that error. So 2-dimensional parity will actually not only detect single bit errors, but it will allow you to correct 2-bit errors, right? However, again, note that this is not very robust. It will also detect I think it will detect all 2-bit errors. You can try out. For example, you could change, say, this to a 0, this to a 1, And even though the row parity won't pick that up, you'll notice the corresponding column parities will pick up that error, right? So in fact, all 2-bit errors will also be detected in two-dimensional parity. I think even all 3-bit errors will be detected. However, 4-bit errors will not be detected. For example, let's use this same case. So if this got flipped to 0, this got flipped to 1, and then this got flipped to 0, this got flipped to 0, right? So in this case, you'll notice neither the row parities or the column parities will be able to detect that. So I think 4-bit errors, it cannot detect all 4-bit errors. But yeah, it can detect 2 and 1-bit errors. So there's a question now whether this is the same as Hamming code. Yeah, it's kind of leading towards that discussion, Daniel. This has some relationship with Hamming codes, but we'll kind of leave it at here because these are fine as toy examples, but you clearly see these may not necessarily be useful in practice. So we need something better. We need something a little better than some of these schemes. Now you might say, okay, how about checksum, right? We've already looked at checksum. We argued that checksum is decent and we've looked at the algorithm. However, still checksum is still not very robust. So it can, the likelihood of errors, erroneous packet scraping, sort of bypassing the checksum algorithm is still fairly high. So the designers of the link layer said they want something which is a little more robust than what checksum is used. And the other point was, since some of the link layer is anyway implemented in hardware, right? So what they thought was, hey, why not basically come up with a scheme that might be more computationally complex, but require less overheads in terms of how many extra bits we add, right? So they are basically trading space complexity, how much extra overheads you create, for computational complexity, because the actual execution can be done in hardware. And that is precisely what's happening today. All the actual error detection algorithm, which is called CRC, which I'll talk about next, is actually implemented on the hardware, on the wireless chip or on the Ethernet chip itself, right? So what is this algorithm, CRC, cyclic redundancy check? It is a fairly powerful algorithm. So I'll first talk about this conceptually. So the idea again is the same. We have some D bits. That's the data that we want to protect. It's a sequence of ones and zeros. There's a generator function that's known both to the sender and receiver. That is of some length r plus 1 bits. And the generator function is known to both endpoints. So since the generator is r plus 1, the idea is that we add some extra bits, one less than the generator function. So for example, if the generator function was 5 bits, you would add 4 extra bits here, append 4 bits there. And we basically deduce, the sender runs this algorithm and it deduces the actual 4-bit pattern, r-bit pattern, I should say, 4 for this example, but in more general terms, the sender deduces an r-bit pattern that should get appended. So that's referred to by this capital R here. So what the sender actually sends is D appended by R, right? So that gets sent out. In mathematical terms, this is when you're sort of left shifting something by R bits. You may remember in binary math, that is equivalent to multiplying the original value by 2 to the power R when you're left shifting by these R bits. And then you have appended a pattern R. So that's basically XORing this value R. Right? So that's the precise mathematical way to denote this. So on the sender end, the question is, how do you choose that R, right? The way CRC works is you choose that R using a certain formula, that certain computation that I'll show you, such that D comma R is exactly divisible by G. And by divisibility here, we mean we are using mod 2 arithmetic. And I'll show you, there's a slide explaining what mod 2 arithmetic actually is. That's the next slide, I believe, right? Now, D comma R gets sent. Now, of course, there could be potential errors. So what the receiver receives is again D prime and R prime. And now the receiver needs to figure out whether there's an error. So what does the receiver do? The receiver takes whatever it has received, divides it by G. If the remainder is non-zero, it knows there's an error. If the remainder is zero, it assumes there's no errors, right? Now, the way CRC works is it can detect all burst errors. By burst, we mean like a block of errors happening, right? We don't mean like one bit is an error here, then there's a gap and there's another bit in error. No, we mean like a sequence of bits being in error, because that is the most likely way errors actually happen in frames. You don't have sort of one random bit here and one random bit here being in error. It's usually like a block of bits that gets flipped, right? So the way CRC, the logic works is that it can actually detect any burst errors that are less than R plus 1 bits, right? So in our earlier example, if the generator was 5 bits, which means R is 4, so it will detect any burst errors of up to 4 bits. It will not be able to detect a 5-bit error, but it will be able to detect a 4-bit, 3-bit, 2-bit, 1-bit. So what is modulo 2 arithmetic before we actually look at an example where in this case, everything is done using mod 2. So which means there are no carries or no borrows when you're doing subtraction. And in fact, all you're doing is you're doing XORs. So what is an XOR? Well, you do a bit by bit XOR. So 1 XOR 0 is a 1, 0 XOR 1 is of course a 1, 1 XOR 1 is a 0, and 0 XOR 0 is also a 0, right? So that's what you see here. So even when you're doing subtraction, you're effectively doing an XOR. Even when you're doing addition, you're doing an XOR. So basically, you're just XORing, whether it be addition, subtraction, or whatever, right? Multiplication is, of course, left shifting by those number of bits, which we have already seen, right? So the way to compute this R-bit sequence that gets added at the sender is the way it works is as follows, right? So we left shifted this by those R bits, and then we are XORing this R. So this is equivalent to if you do an XOR R on both sides, right? So this sort of cancels out, and then this becomes NG XOR R, which is what you see here. And then effectively, if we want to determine R, this means you divide this D times the left shifted zeros. You divide it by G. And then whatever is the remainder is what you would be adding to the at the sending side. So let's look at a concrete example to just make this clear. So imagine this was the original sequence of bits that we are trying to protect. Let's say this is the generator that's known both to the sender and the receiver. The generator is 4 bits, which means R is 3. So we left shift this by 3 bits. We add 3 zeros. And now we divide. And then whatever is the remainder is what gets added at the sending end. So how do we do this division? So as you see here, 1001 times 1 is, of course, 1001. And now remember, we are doing XORs. We are not actually doing subtraction. We are doing XOR. So 1 XOR 1 is a 0. 0 XOR 0 is a 0. 1 XOR 0 is a 1. 1 XOR 1 is a 0, right? So that's done here. Then, of course, like you do with normal division, you bring the next digit down. So we have 101. Now this is, of course, this has to be a 0. This cannot be a 1 because this times 1 is much greater than this. So the next one that you see here will be a 0, right? So that's a 0. So that zeros, 1 XOR 0 is a 1, 0 XOR 0 is a 0, 1 XOR 0 is a 1. Then we bring down the next digit like we do in normal division. And now we try to see if how do we divide this with this? So that will be a 1 now, 1 0 0 1. These two will be zeros. That will be a 1 1. Next we bring this down. Again 1 1 0 would mean this next one is a 0. Then we bring the next one down. Hopefully you're seeing how this works, right? So it's fairly straightforward. Just remember you're doing XORs. So this is what will be the remainder, and this is effectively what is R. So this is what the sender will send. The sender will take this original D and append this. So what would be sent is 1 0 1 1 1 0. So that was the original D followed by 0 1 1, right? So that's D and that's R, right? So this is what the sender sends. What does the receiver do? So the receiver has received this, assuming in this case there are no errors. So this is showing you an example where there are no errors. So you'll notice D and R are unchanged. So the receiver will divide this by G. Exact same logic applies as before. I won't do the whole math for you now. You can do that by yourself. But effectively, you'll see that the receiver will get a 0 remainder, which implies in this case there were no errors, right? So as an exercise, I would encourage you to sort of work through this. Assume, say, a couple of these bits are in errors. Remember, R is 3, right? So this means it can detect all errors up to 3 continuous bits being in error. It can't detect a 4-bit error. It can detect 3-bit errors, 2-bit errors, and 1-bit errors, right? So try it out yourself. Maybe flip 3 contiguous bits and see whether the remainder will still be a 0. It will not, right? Okay, so that's all about CRC. So let's do a quick quiz while we are at this. I think this should be live. Yeah. So it's asking you whether these 3 schemes that we've just looked at, can they always correct bit error, any bit errors? So I'm not talking of 1-bit errors, 2-bit errors. It's a more general question. Can, or no, sorry, it's a, yeah, any, sorry. It means even a single bit error, basically. So it's asking you, can these schemes respectively correct any bit errors? So it could even be a single bit error. The 3 schemes are checksums, 2-dimensional parity, and CRCs. So you would have 3 answers. The first answer would be for checksum, second would be for 2D parity, and the third would be for CRC. Okay, let's have a look. A lot of confusion. Let's see where we are at. So can internet checksums actually detect any bit errors? Well, the answer is no. An internet checksum can only correct any bit errors. Internet checksum cannot correct a bit error. It can detect errors, but it can't tell you precisely which bit was in error, right? You may want to go back at some of those examples and see for yourself, right? You won't be able to tell which bit is in error. You can tell there was an error, but not which particular bit, because in order to correct bit errors, you need to identify precisely which bits were in error, right? So a checksum cannot do that. 2-dimensional parity, your answer would be yes, because as we already saw in those slides, if 1 bit was in error, we could actually have both the row parity and the column parity tell us. So we can actually go and identify that bit and we can go and correct it. So 2-dimensional parity will allow you to correct a bit error. CRC, well, CRC can detect bit errors up to R bits, but it cannot tell you which bits were in error, right? So CRC cannot correct any bit errors at all, if you have seen the algorithm, right? So the answers would be no, yes, and no. So yeah, this middle one. There's a question, James, 2-bit parity can't correct 1-bit errors, though, can it? No, it can. If you go back to this example, that's precisely what we did, right? Yeah. So if you look at this example, so this bit has been flipped, right? This 1 got flipped to a 0. So here the parity, the row parity will tell us that there was an error. The column parity will tell us where there was an error, and you can actually go to the intersection of these two, and you can precisely now say, yes, this bit was an error. So I can go and correct this back to 1, right? So 2D parity can actually correct single bit errors, as it says here. Multiple bit errors, well, it depends. So 2-bit errors, it won't be able to correct. 3-bit errors also. Yeah, so I think from 2-3 bits onwards, it won't be able to correct those. But it can correct, it can only correct 1-bit errors basically with 2D parity. Okay. Now, let's start looking at multiple access protocols. So remember, we talked about 2 kinds of links. So of course, we have point-to-point links, say between routers, or later when we see an Ethernet switch network, you'll see that there's a host that directly connects to an Ethernet switch. You might have seen these examples earlier where you had this switch, then you had various hosts connected to it, right? So this is basically, it effectively becomes a point-to-point link, or even say your ADSL link and so on and so forth. So these are point-to-point links, which means you don't really need any arbitration because each endpoint can effectively send, because most of these links are a full duplex. So both endpoints can send data to each other simultaneously. So there's no real need for arbitration. However, when you have a shared medium, a broadcast medium, which means everyone can hear what's being sent, then we do need a way to arbitrate access. So what are shared networks? Satellite networks, Wi-Fi networks, 4G, 3G, 5G networks. So anything that's using radio transmissions is a broadcast network because inherently you're transmitting your signals as a sort of electromagnetic waves, which means anyone around you can actually hear those signals. There was a way to set up Ethernet networks like shown here. So this was how the first Ethernet networks were actually set up, where you just had this like a bus and you had multiple taps. These were referred to as taps, which would connect different hosts. So this resulted in a shared Ethernet network. Now, normally you don't see networks like this today. You normally see switched Ethernet networks, right? But this is still an example of a broadcast network. Right? I mean, as a human analogy, of course, if you're in a large group and you have multiple conversations going on, then of course that is also an example of a shared network, right? If you may. Okay, so if we have this sort of setting, we want to be able to design a protocol whereby we don't want multiple nodes to send at exactly the same time. So we want some sort of arbitration where we say, hey, you go first, then you go first, then you go first, or something like that, which some way for the nodes to figure out that they do not interfere with some other node that is already transmitting, right? Now, remember, interference is only, you consider it from the perspective of the receiver. So if a node is receiving 2 or more signals at the same time, then we have what is referred to as a collision. Now, mind you, this is not a physical collision. We're not talking about physical objects colliding. We are talking about the signals getting mixed up, right? Whether it be on a wired network or on a wireless networks, we are essentially having a scenario where multiple nodes are sending signals to the receiver, and those signals are now getting garbled up at the receiver, right? So that's what we refer to as a collision. It's not like the packets are physically colliding, right? As the name may suggest. So in this case, we need what are referred to as multiple access protocols, which will decide who transmits. And then if the protocol cannot avoid a collision, it needs to come up with a way from figuring out how to recover from collisions, as we'll see later. So a couple of things to keep in mind. The protocol itself ideally should be distributed. So the nodes should sort of collaborate with each other ideally to figure out a way on who gets access to the channel. And another reminder that you cannot assume that the nodes have some out of band channel whereby they are communicating with each other. So any communication to implement the protocol itself must also happen on that shared channel, right? So that's again something to be aware of. So before we start looking at examples, what may be the ideal properties that these protocols should aim for, right? How do we define what is a good multiple access protocol? So imagine you have a broadcast channel which has a data rate, transmission rate of R bits per second. So these are essentially 4 key properties that we want a good multiple access protocol to achieve. The first one being that if there's only one node wanting to send, so you might have a number of nodes on the network, but at any time, let's say only one wants to transmit, then that node should be able to send at the full transmission rate, right? We should not waste any bandwidth effectively when there's just one node transmitting. When we have M nodes transmitting, now M, so imagine there are a total of N nodes on the network. Now M may be less than or equal to N, obviously. So when M nodes are transmitting, each should be able to send at an average rate of R by M, right? So everyone who wants to transmit should get a fair share of the transmission rate. Now, again, this is on average. We are not talking of instantaneously, so over a reasonable period of time, right? Ideally, it should be, fully decentralized, by which we mean we should not really rely on a special node which is trying to coordinate the transmissions, because then the problem is, what if that node dies, right? And then the network sort of is left hanging. Ideally, we also do not want mechanisms where we need some sort of synchronization between the nodes, whereby we say, okay, this is the start of a slot. This is, you get to transmit for X seconds, then another node transmit, because this means the nodes need to have clocks. They need to be precisely synchronized with each other. And similarly, we don't want any synchronization ideally, right? And then, of course, it should be simple enough to implement, not very complicated. Now, of course, simple is a little vague to sort of define, but let's just go with it for now, right? So there are actually 3 broad classes of protocols that we'll cover. So the first one is something we have already seen. So these are what are called channel partitioning protocols. So they divide the channel into smaller pieces, be it time slots, be it frequency slots, and then allocate pieces to nodes for exclusive use. There is a third kind of protocol, which is referred to as CDMA. You might have heard of this. This is what's used in cellular networks. Now, unfortunately, we won't have time to look into that. But effectively, what they do is they assign special codes to each nodes. These codes are, of course, chosen in a certain manner. And then the nodes can use those particular codes to encode their data and transmit. Okay. The second group is what is referred to as random access. So here you're not doing any division or anything like that. And in fact, you'll see that these protocols do not actually avoid collisions. They will sometimes lead to collisions, but then they come up with mechanisms which dictate how to recover from the collisions. And then, of course, try to minimize those collisions from happening again. The third category is what is referred to as taking turns. So nodes will basically, this is very simple and intuitive, right? You basically say, okay, you go first, then you go, then you go, then you go. So you kind of go around and give each node some time to send data, right? So we'll look through all these in the rest of this lecture. I think this might actually be a good point to take a break. We're just getting about to an hour. So let's have a short break and then we'll start digging into these in a little more detail. For today's meme, it's a bit hard to come up with memes about the link layer, but I found this nice one, which is a interesting joke about security. So this is showing you an Ethernet cable, and it's basically saying cut here to activate a firewall. Basically, it's saying cut your network access, so that way you don't have to worry about security, right? So hopefully you get that joke. Let's just call it. Let's just go for a break now. I'll stop the recording and then we'll recommence in 5 minutes. Record. Okay, we are recording. Right, so let's start by looking at the channel partitioning protocols, and very briefly really, because this is something we've already looked at right at the start of this course. So you may recall TDMA, the idea being that you create these frames. Essentially, the total number of the duration of the frame would depend on how many nodes are in the network, and then you allocate a slice, a time slice effectively to each node. And then you keep repeating this pattern forever, right? So of course, each station gets a fixed length slot, which is effectively the time to transmit one particular frame. Any unused slots, of course, go idle, as we've seen here. So this can be a problem. And then the other issue, of course, is we need time synchronization, right? Because each node needs to be aware precisely these slot times. Otherwise, if their clocks are not in sync, then they might overlap with each other, and that can be a problem. The other way to do partitioning is FDMA. So recall here, we are not partitioning the bandwidth. So each node transmits at the full capacity. Here, what we do is we partition the bandwidth into frequency bands. So effectively, each node gets a smaller fraction of the actual capacity, but then they can keep transmitting over the entire duration of time, right? So in this example, assuming here again there are 6 nodes on the network, you would break up the bandwidth into 6 frequency blocks, assign 1 to each node. We still are faced with the issue of these bandwidth bands going waste if the node is not actually active. We do not need clocks here, but we still need some way for the nodes to know which bands they must be transmitting in, right? So there has to be some way to do these allocations, which can also be a little problematic. So the question again, then going back to the 4 properties we saw, based on this brief discussion of channel partitioning, can you think of how many of these 4 properties do channel partitioning protocol satisfy? And if so, which ones? Now, of course, you won't be able to answer which ones on the poll, but just answer how many, and then we can have a discussion on which of these are actually satisfied. I think this should be active now. I may show you the 4 list here so you know which 4 I'm referring to. Remember the general case, right? We could have n nodes on the channel and m could be less than or equal to n when we say m nodes. So we are not assuming all n, m is always n, okay? M can be less than n. Let's see what you have answered. So many of you are saying 2. So let's have a discussion around that. So if there's only one node transmitting, so which means 1 out of these n, will it be able to send at R? The answer would be no, because either if you're using TDM or FDM, remember we are allocating n slots, right? Or n frequency bands, and only one of them will be used, right? So certainly this is not met in this case. How about the second one? Now again, in this case, if m was exactly equal to n, then this would be true, right? When all nodes that are on the network want to transmit, then certainly each of them will get R by n. However, when m is less than n, this will not be true, right? So in a more general case like this is also not necessarily true. Is it fully decentralized? Well, no. TDM requires some sort of clocks and slots. FDM doesn't need that, but there is still the issue of how do you decide which node is transmitting on which frequency band, right? So there is some aspect of centralization involved there that someone has to come up with that allocation, right? So I would say in general, we could say this is actually not satisfied as well. Well, yeah, it's simple. We can give it that. So the correct answer really should be B, right? In a more general setting. I presume some of you chose 2 because you assumed M was exactly equal to N, perhaps. But remember, in a more general case, M can be also less than N, right? So hopefully that explains the answer. Okay, so that was one family. The second family is what are referred to as random access protocols. So these are fairly simplistic in that they do not assume any partitioning, both in terms of time or frequency bands. The idea is fairly straightforward. When a node has a packet to send, it will transmit at the full channel rate. There is no prior coordination. Now, obviously, this means occasionally you might have collisions because 2 nodes may sense that this is what's referred to as carrier sensing, as I'll talk about. So 2 nodes may sense the channel at the same time, and then they may basically transmit. This is referred to as a collision. And then the protocols itself, they specify how do you detect the collision, and more importantly, how do you recover from collision. So intuitively, when you have to recover from collision, it kind of implies you need to retransmit. So these protocols will sort of advise on how the retransmissions happen. So the protocols that we look at are as stated there. So the first 2, which are kind of linked together, are referred to as the Aloha family. And then the others are referred to as carrier sense, multiple access. And then we'll talk about the differences here as we move forward. So a little bit of history where this whole protocol, the whole family of protocol comes from is can be attributed to this gentleman, Norm Abramson. So he used to work at Stanford and he was sort of involved in some of the earlier designs of the internet protocols in the 70s. He moved to Hawaii. Apparently he liked surfing. And as you may know, Hawaii is a collection of islands, right? And given this, he was working at the university there, and he wanted to set up a packet radio network, essentially a wireless network where they could deploy certain transceivers on these different islands with the central hub in the central campus here in Oahu, so that the nodes could all transmit to the central campus and the central campus could then transmit back to the other nodes. So given this practical setting, he realized that he needed a channel arbitration mechanism, because if two of these nodes started to send at the same time, then there would be a collision. So he came up initially with the Aloha family of protocols. Now, the way I'm going to explain to you these protocols are actually in the reverse order. So I'll first talk of the improved version of Aloha called slotted Aloha, and then I'll explain the original Aloha. So some of the assumptions here are all frames are of the same size. We assume that time is actually divided into slots, and in each slot we can transmit one frame. We assume the nodes precisely know what is the starting time of each slot. So they can only transmit at the start of a slot, not in the middle. We assume nodes are synchronized. And if two nodes happen to transmit in the same slot, then they can detect that there was a collision. So the actual logic is fairly straightforward. So when a node has a fresh frame, in that the network layer pushes down new data, the link layer creates a frame, it will then immediately transmit in the next slot, right? In the next upcoming slot, it transmits that frame. If it detects that there was no collision, it assumes the receiver has received it and moves on, basically. That frame is done. If, however, it detects that there's a collision, then the node will retransmit that frame in the next slot with a probability P. So which means there is some randomness here. So can I ask you the question, why do you think this was random? Why not allow the node to transmit immediately in the next slot with probability 1? In other words, why not make it deterministic, that if there was a collision, then you must transmit again in the next slot? Why do we need a probability P? Yeah, good points. All of you who have answered are spot on, in that if you set this to 1, right, which means a node always retransmits, well, you're setting them up for failure, right? Because if there was a collision, which means we know that there are at least one more node, so at least two nodes trying to transmit. Now, if you say these nodes have to retry again with 100% probability in the next slot, you're effectively creating collisions, right? So which would mean in the next slot, all of them try again, all of them fail, and this keeps happening. So effectively nothing will get sent, right? So to avoid that sort of scenario, the logic is we set a certain probability. Now, how do you set P? I mean, that's out of scope of this discussion. I mean, you could set it to 0.5 or probably depends on how many nodes are really wanting to send at the same time, right? Because if there's too many nodes, you probably want to set the probability a bit lower. If there are only few nodes, you could set the probability a little higher, right? But in any case, so that's the reason certain probability is used, right? So let's first look at how this might actually pan out. So this is an actual example showing you 3 nodes. The assumption is all 3 nodes initially had a frame to send. They tried to send. Obviously, this is a collision indicated by C, which means all these 3 nodes will now transmit in the next slot with a certain probability P. Now, it so happens that, the way the algorithm was executed at each node, none of them decided to transmit, right? Remember, again, because it's based on a certain probability, it doesn't mean nodes have to transmit in the next slot, right? They may or they may not. In this case, it happened that none of them transmitted, so this slot goes empty. In the third slot, it so happened that 1 and 2 decided to transmit, 3 did not, but that still leads to a collision, right? In the fourth slot, it so happened that only node 2 decided to transmit. So this was a success indicated by S. In the fifth slot, remember 1 and 3 still have packets, right? In the fifth slot, neither of them transmitted, again, based on that probability. So this slot goes empty. Sixth slot, both of them transmit together, collision, next one empty, and then eventually here you see successes. Now, of course, this is just an example. It's not always going to be this way, but this gives you an indication that sometimes you might have collisions, sometimes you might have successes, and sometimes you might actually have empty slots, right? Slots is going to waste. So what are the good things and what are the bad things here? Well, the good things here, if you think about it, if there was only one node, right? Imagine there was only one node active at any given time. Then it would be able to transmit at the full rate, right? Because it's never going to experience any collisions. So if there's only one node active and it always has data to send, well, it sends, it keeps sending, right? There's no collisions. So yes, that is a good thing. The other thing is it's highly decentralized. The only assumption we are making is all the nodes know of those slots. They need to be in sync and so on and so forth. And it is certainly very simple to implement, right? With just few lines of code if you were to actually write up code for this. However, there are a lot of cons. So of course, there's still collisions happening, which is bad. Even worse, we are having these wasted slots, which means no one is actually sending, right? So this is actually very bad. Sorry, this one, idle slots. That's what I mean. Collisions, of course, lead to wasted slots, but we are also having empty slots, which is even worse, right? We need clock synchronization, so that is certainly a bad thing. It takes up extra hardware to do that, basically, which adds to costs. The other point is nodes may actually be able to detect collisions, which is basically pointing to something I'll come back to later. But effectively here, particularly if these frames are fairly long, right? These nodes may actually be able to tell that there's a collision somewhere midway through their transmissions. Now there's a related question here by James. How do the nodes actually detect collision? So this goes a little bit into the physics, James. So effectively, when you're transmitting bits, right? So when you're transmitting a signal, what happens in these, particularly in the wired protocols, is you can also activate the receiver at the same time and keep measuring the level of the signal that you're receiving. So as a transmitter, you know the level at which you're transmitting, but if there's another node transmitting, then the combined transmission levels will be a little higher than if just one node was transmitting, right? It would probably be approximately double. So the receiver can measure that and then can tell that, hey, the transmission levels are a little higher than what if I was the only one sending. So that node will be actually able to detect that there's a collision, right? So it goes down to sort of the level of the actual signals there. But the point being that these nodes would be able to detect those collisions much earlier than the duration of this slot, right? Particularly if these frames are reasonably long. So what this means is, if the nodes detect a collision, why do we let them continue here? If the nodes know, say halfway, that there's a collision, then there's no point for them to continue, right? So we'll come back to this point later when we talk about CSMA. So this is again a problem here, right? Okay, so let's do a simple back of the envelope calculation to figure out what is the efficiency of slotted Aloha. By efficiency here, we mean how many. So if we run this algorithm, if we run this example for a long time, right? What is the fraction of slots which are successful, essentially? Because that tells us how much the channel is being utilized, right? So long running fraction of successful slots, assuming there are many nodes to transmit, right? And all have frames to send. So let's, to formulate this, let's imagine we have n nodes and we assume all nodes have always have frames to send. And each node transmits in a particular slot with probability P. Now, mind you, this is actually slightly different from how the algorithm works, right? So as we said, the first time a node wants to transmit, it always transmits, right? So the first transmission is with probability 1. There's no probability there. A node always transmits in the first. However, in this formulation, and then later, if there's a collision, then yes, a node transmits with probability P, right? But what we are kind of taking away that distinction in this formulation. So we say that a node always transmits with probability P, whether it be the first time or whether it be a retransmission. So we are making that slight change because if we don't make that change, it becomes significantly harder to do a back of the envelope calculation. So while this answer may not be exact, it's still a reasonable approximation. So the probability that a node is successful in a particular slot is that that particular node transmits and the other n-1 nodes shut up, right? So they are not transmitting. So if the probability of transmission is P, the probability of shutting up or the probability of not transmitting is 1 minus P, right? So it's basically P times 1 minus P to the power n-1, because all the n-1 nodes are not transmitting. Now this is for one node, right? But for a successful slot, we basically have to look at any node, right? Any node might be successful. And since we have n nodes, and this is the probability of one node being successful, n times of this will be the probability that any node is successful in a given slot, right? So now to find the the maximum value of this, we effectively need to find the probability P that will maximize this equation, because n is fixed, n can't change. So obviously we need whatever we can change is basically P. That is something we can set, right? So the question is, how do we find the best value of P to maximize this? Well, in mathematic terms, that means taking the limit of this as n goes to infinity. Now, again, how we do this, you can go back to your calculus, but I won't be asking you to sort of do all of this in the exam. This is just a simple formulation to explain this. But if you do all of that, you'll see that the maximum efficiency of this is a 1 over E, which comes to about 37%, right? So at best, in the best scenario, we are only utilizing 37% of those slots, 7% of time, right? So this is the maximum efficiency. Now, mind you, this is not that great, right? Which means almost 2/3 of the capacity is being wasted due to collisions, due to slots being idle. Okay. Mind you, this was the improved version, right? As I said, so this was the actual improvement that that fellow Abramson came up with. The first protocol he proposed was even simpler in that it didn't even require any synchronization. So this was what's referred to as pure Aloha or unslotted Aloha. So there was no notion of slots here. When a frame sort of, when a node had a frame to transmit, it will immediately transmit. Doesn't even wait for the start of any slot. Now, this means the likelihood of collisions actually doubles, because imagine, even though I'm using slots here, this is just for simplification. Imagine a node is sending at time t0, right? So this is the particular node that has just sent a frame. So this might collide with any other frame that was currently being transmitted, right? Any time till up to, say, the time for the actual frame to transmit which we are representing as one unit effectively. And it may also collide with any other frame that begins to transmit while this frame is transmitting. So based on that, and based on that math I showed you earlier, I'm not going to repeat it, but effectively the efficiency of this is half of that. So it comes to about 18%, right? So that's the reason he said, oh, this protocol is really bad. So let me come up with this notion of slots that you saw earlier, right? So this was actually an improvement. He doubled the efficiency. So he was a little happier with this, right? Okay. So can we do better, right? So we can certainly do better. And this can go back to some simple, a couple of simple thoughts, right? So in this instance, for example, we saw that here, for example, we said when a node has a frame to send, it transmits immediately, right? Now imagine there was another node that was transmitting. Now, if this node knew that some other node is transmitting, why should it interrupt that node, right? Imagine you're in a conversation, someone else is speaking. Now, you don't forcibly interrupt that other person, right? At least that's not how sort of polite humans behave, right? We do not suddenly interrupt another person. We let them finish their thought and then we speak. So that's precisely what we can also do at the physical, in the link layer, that we sense the channel. If the channel is only sensed to be idle, only then do we transmit, right? So which means we do not interrupt someone else's transmission, right? If the channel is sensed to be busy, then we defer transmission. So that's what's referred to as channel sensing, okay, CSMA. So that's where the name comes from, channel sense, multiple access, right? The second thing we can do is we can also detect the collision earlier, right? So as I noted earlier, when a node detects that there's a collision, which they can typically do within a short time, then now that we know there's a collision, there's no point continuing the transmission because we know it's being wasted, right? We know the receiver is not going to be able to tell because two nodes are sending at the same time. So the colliding nodes, the colliding senders will immediately abort and they will reduce the wastage of the transmission. Now, mind you, this is much easier to do in wired networks and it's much more difficult in wireless networks, right? The reason being that in wired networks, the signals are all sort of confined to the physical link. So it's easy to design hardware to do those signal measurements I was talking about. In a wireless network, if you have at the hardware level, if you're both transmitting and receiving at the same time, right? Your receiver is effectively going to be overwhelmed by the transmitter because they are both sitting right next to each other, if you think about it that way, right? So the receiver is going to have trouble figuring out if there's another node a little further away that's also transmitting because it's so overwhelmed by its local transmitter. Now you can do that, but it requires a lot more sophisticated signal processing and sophisticated hardware. And that increases the costs of these wireless chips. So in most wireless chips, or in fact, all wireless chips today, they don't do collision detection. It's very hard to do, right? So they use a different way to deal with that, which we'll talk about when we look at wireless. So now we'll simply say, okay, this method of collision detection only works in wired networks, right? And again, in human analogy, this is like being polite, right? So let's say there are two people, they speak at the same time in a group setting. They of course can hear that there's another person speaking, so both of them will stop, right? They don't just keep speaking over each other. So that's the same idea here, right? So let's see how this actually works in the context of a real network. So imagine we have this style of the bus-based Ethernet networks that I showed you earlier. So imagine we have this common bus, we have these multiple nodes connected. And so this is the actual physical layout of the nodes. Time here is being shown along the vertical axis. So here, imagine that this node, the second node, starts transmitting at time t0. So it gets a new frame. It senses the channel. It doesn't hear anyone else. No one else is transmitting yet. So it sees no one else is sending, so it can start sending. Right? So this yellow things here, these are the actual bits, if you may, propagating. Right? And remember, we talked about the propagation delay. So the slope here basically depends on the propagation speed and the length. Right? So the bits are now propagating. Right? Now imagine at time t1, this last node here gets a frame from the network layer. So it senses the channel. It doesn't hear anyone. So of course, we can see that this second node is transmitting, but its bits haven't yet reached this node. They have reached this node, they've reached this node, but they haven't yet, at this time, the bits haven't yet, they're still here, right? In fact, they have not even reached this node, if you may, right? So at time t1, the bits from this node have only propagated up to this point, right? So somewhere till here, somewhere till here. So they haven't yet reached this node. So from this node's perspective, no one else is transmitting. So it begins to transmit. And obviously now we have a problem because okay. Yeah, I fixed that. Good scared. Okay. Yeah. Where was I? Right. Yeah. So at T1, as we saw there, this node started sending because it hadn't heard this node's transmission. And obviously we have a problem because both clearly, as we can see here, both nodes are transmitting, and then this is what we refer to as the collision, right? Their signals are effectively being mixed up. So the intended receivers, I didn't really say who is the intended receiver. It doesn't matter. The receiver is going to hear both these nodes, which means the receivers are not going to be able to interpret those packets, right? So this is essentially a collision, right? Now, of course, the exact time and all that will depend on the physical distances. It will depend on the propagation speed, which will determine the slopes of these lines. But regardless, right, you see there's a problem here. This is effectively a collision. So even though we are using CSMA by itself, which is polite in that the nodes are sensing the channel before they transmit, it doesn't stop all collisions. Collisions can still happen, right? So given that these collisions can happen, how do we reduce the duration of time that's wasted? Because if we just allow the nodes to keep sending, you see that we are wasting all this time, right? No transmission is successful till this point, right? All of this time is wasted. So can we do better? So that's where this CD comes in, collision detection, right? So as you see in this picture, this last node began transmitting at T1. However, at this time, roughly here, somewhere here, it is going to hear the transmission from this node. And then it's going to realize that, hey, I made a mistake, right? I started sending, but I can also hear some other node that's also sending. So I can actually abort, right? So it waits a little while just to confirm, because you can't just go on an instantaneous sort of input. It waits for a little bit of time just to confirm that, yes, there is indeed someone else transmitting, and then it aborts, right? So at this point, it's actually stopped sending its bits, as you see here, right? Of course, the bits, whatever has been sent will still continue to be sent. So yeah, sure. And similarly, this node can also do that, right? So roughly around this point in time, whatever this time is, these red bits have now reached this node. It also waits a little while just to confirm, and then it aborts, right? So at this point, the yellow transmission is also aborted. So now here, we have wasted a lot less than here, where we wasted all that time, right? So CD certainly saves us a lot of, improves the efficiency basically, because it's reducing the amount of wasted transmissions. Right? So this is the CD part, collision detection. Right? Now, in terms of the actual practical algorithm, this is precisely the Ethernet version of CSMA CD. Okay, let me take a question there. With the data that is sent at the same time, can the interference be filtered out, or all those packets wasted? So yeah, so this is actually a wasted transmission, right? It cannot be filtered out because the signals are mixed up. So the intended receivers, everyone basically discards this. They detect that there's a collision and they will discard all of this. By doing this CD though, we are kind of reducing that wastage, right? So let's look at the Ethernet implementation of this. Here I'm referring to the NIC. So that is the actual card or the chip that's implementing the Ethernet protocol. So let's say the NIC receives this datagram from the network layer. It creates the frame. It senses the channel. If it's idle, it starts transmission. If it's busy, it keeps waiting until the channel is idle. So if the channel is busy, it just keeps listening and waits till the channel becomes idle, and then begins transmission. Either way, when it transmits, if it detects there's no collision, then all is fine. It assumes it's done with the frame. If it detects there's a collision, what it does is it aborts, and it also sends what's called a jamming signal. So this is just a small signal that's sent just to make sure that everyone else on the network knows that there's a collision. So this is like a confirmation that, yes, there was a collision. Okay, it's a short signal. It's not a long signal. Now, what does it do after aborting, right? So yeah, sure, it's aborted. Now it needs to retry, right? So now how does it retry basically? So to do that, it uses what's called an exponential backoff or a binary backoff algorithm. So the way this works is that because there are at least two nodes that have collided, right? So each node will randomly pick a integer k from this particular set, where 2 to the power m here, m indicates the mth collision, mth successive collision, right? So imagine this was the first collision that happened. So nodes send, they realize there's a collision, they have aborted. Now they want to retransmit. So m is 0. So 2 to the power 0 is basically, m is 1. So 2 to the power m is 1. 2 minus 1 is 1. So initially this set will be just 0 and 1, right? So the two nodes involved in the collision will either pick a 0 or a 1. Then they will count down, basically, which means you wait for this duration of time. This bit time basically means the time to transmit one bit. So 512 bit times means the time to transmit 512 bits on that particular network, right? It's some constant. We don't care. Basically, it's some constant, right? Now imagine both nodes chose the same k, right? So imagine both nodes chose k equals 1 in the first instance. So again, they will count down at exactly the same time. They will retransmit. Again, there'll be a collision, right? Because both nodes chose the same value. So which means now we've had two back-to-back collisions, okay? So the next time they retry, they will not use this set. They will use a larger set, 0, 1, 2, and 3, because m is 2, right? So 2 to the power 2 minus 1 is 3. So the set that they choose from is 0 to 3, okay? Now the likelihood that they will again choose the same value is a little lower, right? Because we are now choosing from we have a greater choice. So for example, one node could choose 3, another node could choose 1, and so on and so forth. However, if again, both nodes chose the same value, it can happen. They'll again collide because they chose exactly the same value. They count down, they collide. Now, the next time they have to choose, because this is now the third successive collision, they will choose a value from the set 0 to 7, because 3 is now M is now 3. So 2 to the power 3 is 8, minus 1 is 7. So this is what's referred to as this exponential back off, right? So if you're having repeated collisions, you keep doubling the size of the set from which you choose these values in the hope that you're less likely to choose the same values the next time around, right? So this is sort of adapting to, if you may, the load in the network, right? If there's lots of nodes wanting to transmit, you'll see that this will increase. There's only few nodes and the likelihood of them choosing the same value is lower. So then you could do with a smaller set in this case, right? So yeah, that's how you retry in this case. So the way to retry is different from slotted ALOA, right? We are not using this fixed probability. We are sort of choosing this, we are using this adaptive dynamic set and choosing a value k from that. Okay? Yeah, and then you basically go back to this step and retry, and you keep doing that, and eventually you'll be successful, right? And then move on, and then you do repeat this for another frame, right? Okay, now in terms of efficiency, what is the efficiency of CSMA-CD? Now, I'm not going to show you how this is actually derived. You don't need to know that. In fact, I'm not even going to ask you specific questions on this. This is just for your information. So it has been shown that the efficiency of this sort of network can be approximated like that, where T-prop is the propagation delay, the maximum propagation delay between any two nodes. T-trans is the time to transmit maximum size frame. And so effectively, because T-prop is usually very low, it almost tends to 0. And T-transmission is usually very high. So the efficiency of CSMA-CD can be fairly high. It can be much higher than 37%, for example, right? So it's much better than ALOA, and it's still fairly simple. And it's completely decentralized, right? There's no notion of slots or anything like that here, right? Okay, so based on this discussion, which of these properties do you think CSMA-CD satisfies, right? So let me just start. And I'll show you that slide again. And as before, M can be less than or equal to N. Let's see, what do you think? So many of you are saying 3, some are saying 2 and 4. So let's have a look, have a bit of a discussion. So if there's only one node wanting to transmit, right, can it send at the full rate? I would think so, right? Based on this, I mean, if there's just one node transmitting, it will sense the channel and it will see the channel is idle, start the frame transmission. For the next frame, it keeps doing that. So if there's no other node, it will never sense the channel to be busy. So it should be able to transmit at very close to R. So I think, oops, sorry, I moved ahead. So I think it would meet this property. If there are more than M nodes, would each node be able to send at the average rate of R by M? Well, when there are M nodes, it means there is likely, collisions are going to be likely, which means we are going to have some wastage, which means we are never going to achieve this, right? Certainly CD reduces the wastage, but it will never we are still going to have some substantial amount of the channel capacity being wasted. So we will achieve fairness in that on average, each node will get a reasonably equal share, but they will not achieve R by M. It will be less than R by M, right? So it won't meet this. Is it fully decentralized? I would think so. There's no notion of clocks or slots. There's no need for any special coordinator. So it meets number 2, it meets number 4. It's simple, right? So I think most of you were right. It meets 3 of those 4, right? Well done. Okay, so now let's look at this last category, which is called taking turns. So this is sort of trying to take the best from the channel partitioning and random access. So if you remember what channel partitioning is, it can share the channel efficiently and fairly at high load. So effectively, as when M is very close to N, channel partitioning tends to be good. However, when M is much lower than N, then we are wasting a lot of capacity, right? So it's not very efficient. Random access is actually efficient at low load. So when there are only a handful of nodes, or maybe one node, or maybe 1 or 2 nodes, they can generally get good use of the channel. But at very high nodes, there's a lot of collision overheads, right? So taking turns is trying to sort of achieve a balance between both. So there are 2 broad categories of these. So there's one category which relies on polling. So effectively here we have a hierarchy. So there are some more capable nodes and some less capable nodes. So we'll call this capable node as a captain, the less capable node as conscripts. These are respectively dumb devices. And the captain is then responsible for polling these devices. And when they're polled, they will send data, right? And then captain can poll another device, can send data, right? And so on and so forth. So again, this is simple, but then there are some concerns, right? There is this overhead of the captain having to poll, which can use up some capacity. There's the question of latency. So a node cannot immediately transmit data. It needs to wait till it's polled. And then what happens if the captain dies, right? Then we are left without a captain and we run into issues. So yeah, there can be some problems with this. That said, this type of protocols are used, particularly in the context of Bluetooth networks, right? All of us have various Bluetooth devices, and usually you'll see that there's, for example, if you're using a Bluetooth keyboard, a Bluetooth mouse, then your laptop or your desktop, your machine basically becomes the captain. Your keyboard and mouse are the conscripts, right? And your captain, your machine is basically polling these peripherals, and they then send data and so on and so forth. Now, mind you, this is happening at a fairly small time slot, so you probably don't even notice these delays in practice, right? The other option is to use what's referred to as token passing. So here there's a special control token that's passed from one node to another. When a node wants to transmit data, it captures the token. In this case, if the node has nothing to send, it just passes it as on. The next node, which gets a token, wants to send, so it holds on to the token, sends data, and then, sorry, skipped over that. I don't have an animation, but then it would release the token, right? And so on and so forth. Now, what are the concerns here? Well, there's this overhead. Again, like before, like in that polling mechanism, you have to wait for this token to pass around. There's some latency. There's also the possibility of a single point of failure. So what if a node captures a token and dies, right? So then there's no more token being circulated. Then what do the other nodes do, right? So this can again be a problem. Now, in fact, there was a very popular link layer protocol called Token Ring. So in the 70s and 80s, Ethernet and Token Ring were sort of competing with each other. For various reasons, Ethernet won. So you don't really see Token Ring networks that are actually implemented. There's a question here, would separate Bluetooth networks interfere with each other? Yes, they would. We'll talk briefly about this when we get to Wi-Fi, but effectively, if you have these disparate Bluetooth networks, right, the way they are normally set up is in Bluetooth and Wi-Fi, we break up the broader channel into smaller, the broader frequency range into channels, and then each network will operate on a different channel. So as long as they pick channels that are not overlapping, they will not interfere with each other. Right. We'll talk briefly about that when we talk about Wi-Fi. Okay, now in terms of a practical protocol, of course, we've looked at Ethernet. Another practical protocol to consider is cable access networks. So remember earlier, we talked about cable as a way to access the internet. We talked about this. So this is your home. You have your coaxial cable coming in. There's a splitter. Part of the channels are sent to your TV. The other part go to your cable modem and use for transmissions, right? And we talked about how this coaxial cable then runs to a cable head end, and then a single sort of head end is actually servicing many houses, many units in a particular area, right? So if you look at how cable works, so you have basically, if you look at the downstream part that's coming to your house, you have TV frames, TV channels coming in, you have the actual internet frames, and you also have some control messaging that's coming down, right? So the way this is actually set up is the channel is actually broken down. So they use FDM essentially to break up the channel into various downstream channels. There's also various upstream channels. And the way this works is for upstream data, the users are actually contending using some sort of random access protocol for certain time slots, and others are assigned using TDM. So this is, I'm not going to go into this in any detail. You won't get any questions on this. You can certainly read this up in your own time, but this is an example where all of these concepts are actually used. So this protocol, which is called DOCSIS, it's using FDM for the upstream and downstream frequency channels. As we saw when we discussed this earlier, certain channels are set aside for upstream, certain channels are set aside for downstream. And then within those channels, they're using TDM. So they're then splitting up the time into slots, and then these slots are being allocated, particularly in the upstream part. The upstream data is using some aspect of TDMs. Right? So yeah, this is just to sort of hint at what's actually used in some of the, in a practical protocol like DOCSIS. Okay, now that we've looked at taking turns, of course, we need to complete the loop here and see if taking turn protocols actually meet which of those requirements do they actually meet? So could you have a crack at this? Not many responses, but let's go with what we have. So many of you are saying 2, some of you said 1. Okay, if only one nodes want to transmit, can it send at R? Well, strictly speaking, no, because there's some overhead. Remember, there's either whether you're using polling or whether you're using tokens, there will be a little bit of overhead to send that token around. If you assume that overhead to be low, you could say yes. So this is kind of either yes or no, depending on how you exactly interpret that. When M nodes want to transmit, can each send at average R by M? Again, there won't be collisions, certainly, but there will certainly be a little bit of overhead again for sending that token around or for that polling. So it really depends how you're factoring in the overheads, I think, here. So it's a bit imprecise, unfortunately. Again, if you had explained your reasoning, I would agree with either of these answers, depending on, provided you're giving satisfactory explanations. Is it fully decentralized? No. In the polling one, you do need a dedicated captain. Even with token ring, there is this special token that needs to be circulated, and that is in a way sort of could be considered an aspect of centralization. So it perhaps doesn't meet 3, I would say. It is certainly simple, right? So really, you could, if you assume these to be no, you could say 1. If you assumed these to be yes, you could say 3. Or maybe if you assume one of them to be yes. So really, it depends a little bit here on how you interpret these two, right? There's a question, isn't the error recovery complex, so it's not simple? Well, the error recovery applies to everyone, right? Here, if you're talking of CRC, that's some, I mean, here the question is, we are not focusing on the error recovery, right? This is more about arbitration. So the simplicity here is referring to the arbitration, who gets to send next, right? We are not, this is not a, we are not answering this for the entire, all the functions that a link layer can provide, right? This is this whole discussion is completely independent of error recovery. I meant if a node dies. James is saying, okay, so you're referring to the fact of recovering. So I think that kind of would go into this argument, right? Where by simplicity, again, we are referring to the MAC part of it. How do you recover from, say, the captain dying, or how do you recover from a token that's captured and not released? Sure, that may not be simple, but I think that could be attributed to not meeting number 3, perhaps, right? Yeah. So in any case, you see that again, the bottom line is none of these protocols are actually meeting all 4 properties, right? So there's always some trade-offs involved. So I guess you saw that CSMA-CD met 3. This could meet 3 depending on how the specific context in which this is implemented. So that's the reason you see in practice, we see protocols like that being implemented. You see some of these ideas being implemented in protocols like Bluetooth and so on and so forth, right? And even some of this could be implemented in protocols like DOCSIS, as you saw. So it's really sort of horses for courses, as they say. Okay, I think that's a good point to stop. So let's conclude the lecture. A perfect point in terms of the content. We can start looking at local area networks, addressing Ethernet, and so on and so forth on Wednesday. So have a great week. I'll hang around for a minute if there's questions. If not, I'll see you all on Wednesday and on the forums. Why are there 2 same lag6 links on the web CMS page? Okay, I'll have a look. Perhaps both Heda and me responded to one of those queries. I'll have a look. We'll fix that up. Okay. Bye, everyone.